Okay, here's your introduction to energy in the physical states of water. What we're dealing with is specific heat capacity. We've already worked with our metals this week, but you guys know that Q equals M times C times delta T. That'll tell you how much energy it takes to heat up and cool down a specific substance, and with its own individual specific heat here. Specific heat is different for ice, water, and steam. And let's talk about that now. The melting point of and freezing point of water is 0 degrees. So that means when you're below 0 degrees Celsius with water, it's going to be in the ice form, in the ice stage. I'm going to go ahead and write down ice here so you guys know what I'm talking about. Now, this is temperature on the y-axis and energy on the x-axis, and say if you're about negative 20 degrees, you're going to be in the ice stage, and any energy that you input into the ice will raise its temperature. Now at that stage, any energy that goes in, we're going to say that it's thermal energy, and thermal energy change makes the particles move faster. And we all know that temperature is the measure of the average kinetic energy of the particles. So energy that goes in just makes them go faster. Okay. Now once you get to 0 degrees Celsius, what you have there is 0 degree ice still. Okay. Now once you get to that ice stage, any energy, or 0 degree ice, any energy that you're inputting into the system is going to go to changing its phase. And we're going to say that that's going to be a change of phase here, where phase energy changes the attractions and the bonds. Okay, so it's changing its form. And in this stage, what you'll have is, instead of having ice bonded together, the energy that goes into it is actually going to break those bonds, and I'm going to put EPH right there. And at that stage, the energy that you're putting into it is not raising the temperature anymore. Here in the ice stage, any energy that you put into it would increase the temperature. Once you get to here, the energy that goes into it is changing its form. Now at the end of this stage, that's going to be water. Okay, you're going to have 0 degree water. Okay, now after that, what's going to happen is you have water, and any energy that you put into it is going to heat up that water. And so I'm going to increase the thermal energy here. I'm going to write ETH. Okay, now after that, once you get to 100 degrees, you're going to have another flat point. And at this flat point, the energy that you put into it is going to change the water into steam. So we have ice here, we have water here, and then we're going to have another phase change at 100 degrees, because we know that water boils at 100, and any energy that you put into it is not going to raise the temperature of 100, raise the temperature at all. But the energy that you're entering into it is going to be used to change it into steam. Okay, and again, like we said, the EPH changes the bonds between the molecules themselves. So I'm going to put this here as ETH. Okay, so just to recap a little bit, when you're below 0, you're at your ice, and energy you put into it is raising its temperature. Once you get to this point, you are 0 degree ice. And then energy that you put into it changes its phase, and then you'll have 0 degree water. If you notice, maybe you have an ice cold lemonade drink and you put ice in it, it gets pretty cold. But you'll notice that it stays nearly the same temperature until the water is, or until the ice is almost gone. But then at that point where you have 0 degree water, any energy that you input it will raise its temperature. And of course at this point you'll see some particles of steam, but once you get to 100 is where you have that rippling boil effect. and any energy that you put into it will not make it any hotter than 100 degrees Celsius, but it'll change the bonds and turn it into steam. Okay? And then at this point, this is all 100% steam. Just imagine that we had this trapped in a chamber, and then, and none of the steam could release. Well, then you could heat up that steam upwards of whatever temperature you want. Okay? Now those are the 5 stages. Okay? I guess it's important to note that we're going to have specific units down here. So let's talk about these equations for a second. Q, it is going to have a unit of joules. As we know, the joules is a measure of unit of energy. M is going to be grams. C here is specific heat. Now, specific heat capacity changes depending on whether it's ice or water or steam. Now, this specific heat at ice is going to be 2.0 joules per gram degrees Celsius here. Okay, water is 4.18 joules per gram degrees Celsius, and steam is 2.0. Actually, I'm sorry, I apologize. Down here is 2.1 joules per gram degrees Celsius. Okay. Now this is C for specific heat, for the Q equals MCAT equation. So when you're having a thermal energy change, when you're actually changing the temperature here at ice, water, and steam, you're going to use MCAT. And then at these phase changes, you're going to use this equation here. At this stage, you're going to use the heat of fusion. The heat of fusion is 334 joules per gram. And then at this stage here, where you're actually vaporizing it, you're changing it from water to steam. That'd be vaporization. That's why they call it HV, heat of vaporization. And that value is 2,260 joules per gram. Okay, and if you're going in this direction, it's called vaporization. If you're going in this direction, it's condensation. The same thing as this is, if you're going in this direction, this is melting, and if you're getting colder, it's freezing. Now, this brings me to another point. If you're putting energy into the system, say in an MCAT, where say you start at 20 degrees and you go up to 80 degrees, well, your final temperature, if you're going in this direction, is going to be 80. So in this equation here, you're going to have 80 minus 20 degrees. And you would use the specific heat of water and plug that in there. And you'd also say, oh, if it's 100 grams, plug that in there. So if you do 80 minus 20, that's going to be a positive value. And if you're inputting energy, that's what you want. It's going to be a positive amount of joules. But if you went the opposite direction, where your final temperature was 20 and your initial was 80, you would say it was 20 minus 80. And that's going to give you a negative value, and that's what you want, because you're actually taking heat away. Okay? Now, for this equation here, you can't have a negative unless you recognize, okay, well, if I'm heating it up, it's going to be a positive value. If I'm taking away and freezing it, it's going to be negative. So in order to have the correct sign for joules, you just have to recognize, oh, if it's freezing, you just throw in an extra negative there. And if you're increasing it or melting it, it's going to be positive. So in a nutshell, when we do these problems, you're going to want to know where you start and where you end. And the most complicated problem we'll ever get is if you start with a negative degree ice, and then you melt it, and then you heat it up, and then you vaporize it, and then you heat up steam. But that's the basics there of the phase changes of water and the energy involved. I will say that it will be very important for you to be able to recreate this heating curve and cooling curve in order to do well on the problems and on the test. All right, thank you.